So now that we understand a little bit about polarity and the idea of an unequal sharing of electrons within a bond, we can start to think about how that would affect an entire molecule, as we have generally multiple bonds within a molecular species. And that's really the thrust of section 5.8 here, where we start to talk about the shapes and polarity of molecules and apply those electronegativity principles from the last section and understand how that will affect the shape and overall polarity of the molecules in this section. One of the key bonding theories that will help us to arrive at these shapes of molecules is valence shell electron pair repulsion theory, or VSEPR. Sometimes people will call it VSEPR, but it's not really VSEPR, it's VSEPR. So I play it safe and I always just refer to it as VSEPR theory. Okay, so in this theory, valence shell electron pair repulsion theory, we consider that central atom and how the electron groups around that central atom should be arranged. And of course, since they're electron groups, they will repel each other. So we want to have them arranged as far apart from each other as possible in three-dimensional space. Remember, a lot of these depictions are in 2 dimensions, but molecules are 3-dimensional, so don't forget to use all that available space. We also want the electron groups to have the least amount of electron-electron repulsion, and especially if they're lone pairs. Lone pairs have even greater repulsion than bonding pairs. Finally, we can use this ideal arrangement of the electron groups around the central atom to predict our overall molecular shape. And here we see it in italics, right? 3-dimensional shape of the molecule can be predicted by looking first at the number of bonding groups and lone pair electron groups around the central atom, and then applying this VSEPR theory, which gives us a framework of what we should expect for a given number of groups around any central atom. So let's start with a simple case where we have just 2 electron groups around the central atom. So in a molecule of beryllium chloride, remember beryllium from our list of exceptions there to the octet rule, beryllium's happy with a quartet. So in beryllium, if we have just 2 electron groups around that central atom, the beryllium itself would want to have those electron groups as far away as possible. So to minimize those repulsions, as we see in our picture there on the screen, the arrangement of those 2 electron groups is 180 degrees, or completely opposite one another, and the shape therefore is linear. We get a straight line relationship between chlorine 1, the beryllium center, and then chlorine 2. That's the best way in 3 dimensions to separate the electron density and minimize those electron-electron repulsions. So we get a linear molecule in the case of our 2 electron groups about the central atom. If we increase it to 3 electron groups, now let's consider boron trifluoride here. Remember, boron was one of our other exceptions to the octet rule. We had the 3 exceptions that have less than an octet: hydrogen, which is happy with a duet; beryllium, which we just saw is happy with a quartet; and now boron, which is happy with a sextet. Of course, boron can also obey the octet rule, whereas hydrogen and beryllium do not. So boron's a really interesting and versatile element, and certainly not boring, as sometimes people might think by the name boron. So if we look at the electron dot formula, we would make it look sort of like a T shape there if we use our standard drawing scheme. If we want to separate that out to minimize electron-electron repulsions, we make what's called a trigonal planar shape, where we've separated those electron bonding domains around the central atom by 120 degrees. So we've maximized the 3-dimensional space there, and we have now the repulsion minimized by maximizing the distance, the bond angle between those electron groups. And of course, as I've just said, the shape is trigonal planar. So there's 3 different species about the central atom, and they're all in one plane, the plane of the screen here, as we see in this 3 electron group domain. Now, so far we've discussed electron groups as being bonding groups, and that's not always the case. Sometimes we have a lone pair on that central atom, And so if we look at the molecule of sulfur dioxide here, the sulfur has 3 electron groups around itself, 2 electron groups that are involved in bonds, one a single bond and one a double bond, but as we said with resonance it's more like 1.5 bonds each. But there's also a lone pair on that central atom, so the sulfur has the lone pair as well as the 2 bonding groups. So in order to minimize repulsion, again, we've said that in the case of boron trifluoride that we just talked about, we do that trigonal planar arrangement, 120 degree bond angles. In the case of sulfur dioxide here, instead of being trigonal planar, which is the arrangement of the electron groups, we're what we call bent in terms of molecular geometry. So those are 2 different distinct ideas. Sometimes they're the same, sometimes they're different. In the case of boron trifluoride, our electron geometry was trigonal planar and our molecular geometry was trigonal planar because we had all of our electron groups as bonding groups. In this case, where one's a lone pair, we still have the electron groups in a trigonal planar arrangement, but the overall molecular shape is what we call bent because we only consider the bonding groups in molecular geometry. Also, with the presence of that lone pair, the lone pair is greater repulsion than bonding pairs. So actually, we've constrained that OSO bond angle to slightly less than 120 degrees, and we have, again, that defect as a result of the larger repulsion due to a lone pair than a bonding pair. Okay, so be aware that molecular geometry and electron domain geometry do not always have to be the same. When you have lone pairs, typically they will be different names. Still trigonal planar arrangement for the 3 electron groups, but now since 2 are bonding groups and one's a lone pair, we have a bent molecular shape. Okay, if we go up to 4 electron groups and we look at a molecule of methane, CH4, this is, again, for those of you headed into 142 after 141 here, this will be a very important idea because carbon tends to make 4 bonds, and we tend to look at oftentimes this geometry. So 4 electron groups around the central atom. We draw it there at the bottom left like it's sort of a square shape or a T shape. But in reality, that's not the best we can do, right? In 2 dimensions, that looks good. It looks like everybody's as far away from each other as possible. Those are 90-degree bond angles, though. If we consider that we have 3 dimensions, the tetrahedron is actually the optimal way to organize that geometry, the pyramid-type shape. And so that allows for bond angles of 109.5 degrees, and that's certainly better than 90-degree separation. So if we have 4 electron domains around a central atom, we'll expect a tetrahedral electron domain arrangement, and if they're all bonding pairs like they are here in the case of methane, we get a tetrahedral shape. And if you look at the very last image there, the tetrahedral wedge dash notation, that's what you'll see a lot in 142. And again, what we're showing with the straight lines, those are in the plane of the screen, and then the wedge there, the filled in wedge, is coming out at us, and the dashed line is going back into the plane of the board here. So it's a nice way to try to show 3-dimensional geometry when we're dealing with 2-dimensional planes. Well, just like the case of trigonal planar electron domain geometry, when we had a lone pair, things were different than when we had all bonding pairs. The same is true for the tetrahedral electron geometry. If we have 4 electron groups with one being a lone pair, our classic example is the ammonia molecule. So we have 3 electron groups involved with that NH3 bonds, and the 4th electron group is a lone pair on the nitrogen. So in order to minimize those repulsions, we've already mentioned that the best way to have 4 groups around a central atom in 3-dimensional space is a tetrahedral arrangement. In this case, because the molecular geometry is only defined by the bonding groups, those 3 bonded atoms of hydrogen to that nitrogen center form a pyramidal shape. So just like we had the trigonal arrangement with BF3. That was trigonal planar. This is still trigonal because it's NH3, but now we call it trigonal pyramidal because it's not all in one plane, like the planar case of BF3. The hydrogens and the nitrogen are actually in different planes, and it's a pyramidal geometry. So we see at the far right that trigonal pyramidal wedge dash notation. We have the one NH bond in the plane, another coming out at us, and still a third going back away from us. So sort of like a pyramid with now just the three bonding groups, the one lone pair that doesn't influence the molecular geometry. And what if we have still 4 electron groups, but now 2 lone pairs? So this gives us our good friend, the water molecule, good old H2O. So in the case of H2O, we have 2 electron groups, which are HO bonds, and then 2 lone pairs. So we still have a total of 4 electron groups, and we know those 4 electron groups should arrange themselves in a tetrahedral arrangement, so that's the electron domain geometry. But in terms of the shape of the water molecule itself, if we ignore those 2 lone pair groups, then we have what's known as a bent shape, sort of like the SO2, right, that we also called bent, but this time our bent angle is somewhat less than 109.5 degrees. In this case, we have 2 lone pairs repelling, so we're actually down to about maybe 104.5 degrees bond angle for the HOH angle in the water molecule. Again, slightly distorted, slightly lessened to allow for those electron-electron repulsions among the lone pairs, which tend to be greater than among bonding pairs. So in the SO2 case, it was bent with an angle slightly less than 120. Now we're bent with an angle somewhat less than 109. So difference there, of course, is that in the SO2 case, we had a total of 3 electron groups, 1 being a lone pair. This time we have 4 electron groups, 2 of which are lone pairs, and the other 2 bonding pairs. And so here in table 5.16, we have some molecular shapes for 2 and 3 bonded atoms. So in the case of the 2 electron groups, we're a linear shape, and beryllium dichloride or beryllium chloride, if you're going to use the nomenclature for ionic or covalent, right? We'd probably say ionic because it's a metal and nonmetals, but the fact that we're talking about molecules suggests that it's a covalent bond. So we name it both ways, actually. Beryllium chloride and beryllium dichloride are both ways that you'll hear that named, but again, it's sort of exceptional, and I won't bog you down with those details come exam time, but it is good to always be thinking about that sort of thing. The other thing we don't even talk about is, what if one of those was replaced by a lone pair? Well, of course, we'd still be linear, although we wouldn't have a second bonding group. If we look at the trigonoplanar electron domain geometry, well, that can give rise to a molecular shape that's either trigonoplanar as well. If we think of the BF3 example, where all 3 electron groups are bonding groups, or in the case of SO2, where we have 1 lone pair and 2 bonding groups, we get a bent shape. If we were to go ahead and replace another bonding group with a lone pair, we'd have just 1 bonded atom. And again, whenever we have just 1 central atom and 1 bonding atom, it's always going to be a linear arrangement. So we don't show that here, but obviously that should be fairly logical for you. As we move up to now 4 bonded atoms, again, the electron group arrangement would be tetrahedral in all cases here, but as the number of lone pairs increases from 0 to 1 to 2, or even to 3, if you think of, say, an HF molecule or HBr, you'd have 3 lone pair groups and 1 bonding group. As I said, whenever there's just 1 bonding group, it's always going to be a linear type molecule. But realize any of those would be examples of the electron group arrangement of a tetrahedron. But if they're all bonding atoms, like methane, CH4 here at the top of our table, we would also have the same molecular shape as the electron group arrangement. Once we start to introduce lone pairs, our molecular shape changes. As we get 1 lone pair and 3 bonding groups, like in ammonia, NH3, we now get what's called trigonal pyramidal molecular geometry. And then finally, the last one we discussed, which was the water molecule, 2 bonding groups, 2 lone pairs, a bent molecular geometry from a tetrahedral electron group arrangement. This is as far as we go in the course. There are higher level shapes, things like square pyramidal arrangements and octahedral arrangements, but we don't really discuss those. We're mainly focused on tetrahedra or trigonal planes or linear type arrangements, and then the molecular shapes that can be built off of those electron group shapes. Because the tetrahedral geometry is what we're going to max out as for Chem 142. So hopefully this is in detail enough for what you'll need later on. If not, you'll go on to a higher level chem class and you'll certainly talk about those larger electron group arrangements there. Okay, so as we've done frequently in the course here, we'll have a guide to how we might predict molecular shape from the VSEPR theory. And our guide to predicting those molecular geometries involve first drawing that electron dot formula. So if you still haven't got that skill down, please make sure to practice it. Reach out to me for help, because if you can't do that, then you're not going to be very successful with the next steps. Okay, so as long as you've drawn that correct electron dot formula, you can go ahead and arrange those electron groups around the central atom to minimize electron-electron repulsion. And finally, our third step, we'll use the bonded atoms to the central atom to determine the molecular shape. So step 2 is when we get our electron group geometry. Step 3 is when we get the molecular geometry, which is only different if we have lone pairs to consider. Okay, so let's take a look at an example of this. So let's predict the molecular shape of H2SE. So step 1, first we would draw the electron dot formula. So because selenium's in group 6A or group 16, we know that we're going to have a total of 6 valence electrons there. Hydrogen, being in group 1, has 1 valence electron. We have 2 atoms of hydrogen, so each brings its 1 electron for a total of 2 electrons from the hydrogen and a total of 8 electrons altogether. And so we get the Se single bond to each H, and we know we're done with hydrogen there. It can only hold a duet, at least for our purposes. And that leaves us 2 lone pairs around the central selenium. In our next step, we look at arranging those electron groups around the central atom to minimize repulsion. So because we have 4 electron groups, we would expect a tetrahedral electron domain geometry, or a tetrahedral arrangement of those electron groups, just like in water. And that shouldn't surprise anyone, right? Selenium is in the same family as oxygen, so H2SE should be a similar shape to H2O. So finally now we're ready for step 3. Because 2 of our 4 electron groups are bonding groups and the other 2 are lone pairs, we'd expect H2SE to have a bent shape, just like water, with a bond angle of somewhat less than 109 degrees. So hopefully that was fairly straightforward, and working through how we apply that guide to predicting molecular geometries, because we're going to follow up here with a learning check. Okay, so now your challenge is to determine the shape of a molecule of NF3, and you'll determine if it's A, linear, B, trigonal pyramidal, or C, bent. And go ahead and pause the video here, and when you're ready to check your answer, please start back up. Okay, so step 1, we'll draw the electron dot formula. Nitrogen's a group 5 element, or 5A I should say, or group 15. We have 5 valence electrons. Fluorine is a group 7A or 17 element, so 7 valence electrons, but we have a total of 3 fluorine atoms, so 3 times 7 gives us 21, plus the 5 from nitrogen gives us a total of 26 electrons. We know we need to make at least 1 single bond between each N and F, so that uses up 6 of our electrons, leaving us 20, right? 26 minus 6 gives us 20, so we take those 20 and we complete lone pairs around each fluorine atom. So that uses up 18 to complete the octet on each of the peripheral fluorine atoms. And finally, we have 2 electrons left to have a lone pair on the central nitrogen and complete the nitrogen octet. Okay, so in our next step, we have 4 electron groups around a central atom, so we would expect a tetrahedral arrangement of those electron groups. So now we're ready to move on to step 3. Because one of those bonding groups was a lone pair and the other 3 are bonding pairs, we would expect NF3 to have a trigonal pyramidal molecular geometry with a bond angle of somewhat less than 109 degrees. So again, it's just a matter of getting used to these patterns, and also you see it. NF3 looks like NH3, right? Although it also looks like BF3 if you're not careful. So just realize that getting the right Lewis structure drawn, those electron dot diagrams, those are critical because that will lead you down the path of either 2 electron groups, 3 electron groups, or 4 electron groups. Then it's time to consider if there's any lone pairs present, because that will influence the geometry. If there are lone pairs, the molecular geometry will be different from the electron group geometry. So now that we have an idea, at least hopefully you'll continue to practice and become experts at those molecular geometries, but at least now we have an idea of how to come up with the molecular geometry based on a given formula for a molecule. Now we're ready to consider if the molecule has polarity. So when we talk about a polar molecule, first of all, we've got to have something that contains polar bonds. Okay, you can't have a polar molecule if you only have nonpolar bonds. So if we think about, say, the H2 molecule or any of the diatomics, they have a 0 electronegativity difference. It's the same atom bonding with another atom of its same type, and they're always going to share equally. So we've got to have polar bonds, which means we have to have 2 dissimilar atoms involved in the bond. Secondly, we have to have a separation of positive and negative charge, right? A dipole, if you remember that phrase from earlier in chapter 5, where we show either the delta plus and the delta minus, or we show the arrows with the plus end and the arrowhead. And finally, we have to have dipoles that do not cancel. If we have dipoles exactly opposite, if you think about that beryllium chloride molecule we looked at first in this chapter, that would have a polar bond. The BeCl bond has a pretty significant electronegativity difference, but you've got one pulling in one direction where the chlorine's grabbing those electrons more of the time and that unequal sharing, but at 180 degrees you have the same thing happening and therefore they cancel out. If we look at HCl or NH3, the dipoles don't cancel because we don't have anyone pulling equal and opposite net cancellation. So of course the nonpolar molecule would involve either nonpolar bonds or a symmetrical arrangement of the polar bonds, at least an arrangement that allows for a net cancellation of dipoles. So if we look at the CO2 molecule, for instance, that has a very similar situation to what I just described for beryllium chloride, where you have a carbon-oxygen electronegativity difference of a whole unit, right, a 1.0 unit difference, but you have the pull of the oxygen to the right being canceled by the pull of the oxygen to the left, so there's no net polarity. It's a nonpolar molecule for CO2. Likewise with BF3, it's not as easy to see, but you do have each of the BF bonds, the fluorine's winning that tug of war. It's having the electrons more at the time, so one's being pulled straight up, and then one's being pulled down to the left, one's being pulled down to the right. So altogether, there's a net cancellation. If you know your vector sums, and any of those who've taken physics probably have at least heard that term, and depending on how well you did, you may have enjoyed that course. But that's the sort of thing we're looking at here, is the vector sum would be a net zero cancellation. Finally, the CCl4 molecule is also nonpolar because you've got all those CCl polar bonds being canceled by equal and opposite dipole moments. Alright, so like we had before for many other parts of this chapter and the whole text so far, here's a guide for determining molecular polarity. So first we have to determine if the bonds are polar covalent or nonpolar covalent. If they're ionic, we don't have a molecule anyway. But once we make that determination, if we only have nonpolar bonds, we can't have a polar molecule. If we have polar bonds, that may lead to a polar molecule because we have to consider step 2. If the bonds are polar covalent, then we have to draw the electron dot formula and determine if those dipoles cancel or not. Is there a net direction where the electrons are being pulled, or does the pull in one or more bonding position equal and opposite to the pull in other bonding positions? Okay, so let's work an example together, and we'll use our good friend water. If you never had a chemistry course before, you might think that water is arranged in a straight line, right? HOH. Sometimes we even write it like that in chemistry, but it's very important you understand that it's not arranged that way, because water is indeed, as we'll find out, I hate to spoil it here, but here's your spoiler alert, because I'm going to tell you right now that water is indeed polar. So step one, first we'll determine if the bonds are polar covalent or non-polar covalent. And here with the OH bond, we have a very significant electronegativity difference of 1.4. So it's quite a polar bond for each of those OH bonds. Now here in step two, if the bonds are polar covalent, we can go ahead and draw the electron dot formula and see if the dipoles cancel or not. So because we have 4 electron groups around that central oxygen, we can draw 2 in the plane at an angle of about 104.5-ish for water. So we have the HOH bond there, and the oxygen is actually winning. So that's probably the first time we've seen the central atom being the one that holds the electrons more of the time. But so you've got the OH bond pointing toward the O for each side, and they can't cancel each other that way. If they were pulling the other way, yes, but since the oxygen's the one that's pulling the electrons toward itself and becoming the partial negative, we have a buildup of partial negative at that oxygen, right? Sort of straight up in between those OH bonds for the net vector. And therefore, because there's nothing pulling in the opposite way to cancel, we have ourselves a polar molecule with a partial negative end at the oxygen and partial positives at each of the hydrogens. Okay, so now it's your turn to see how well you do. In this learning check, you're going to determine the shape of each of the following molecules, and you'll also determine whether they are polar or non-polar. Explain why you made the determination for each of those molecules as either polar or non-polar. It's a good time to pause the video. This should take you a while. When you're ready, start back up and we'll see how you did. Okay, and there we have it. Let's just talk through them one by one. The PBr3 molecule is pyramidal, and it is therefore polar. The dipoles don't cancel, and the big giveaway here is that lone pair you should have had on the phosphorus, right? It's going to look a lot like ammonia. NH3 has the lone pair on the nitrogen and each of the bonds to hydrogen. Here, phosphorus is going to have a lone pair and 3 single bonds, one each to the bromines, and the bromine's going to win that tug of war a little bit. It's going to develop a partial negative. The phosphorus will develop a partial positive. There's nothing straight up to cancel out that partial negative, and therefore we'll end up with a polar molecule because we don't cancel the dipoles. Number 2, HBr, that's going to be linear, right? We said that whenever there's just 2 atoms involved, that we're always going to have a linear type molecule. So this would be an example where we have a central atom. I guess if you want to consider the bromine central, because we only have two atoms involved, the bromine would have 3 lone pairs, and then there's the 1 bonding pair to hydrogen. Okay, so we have the bromine pulling the electrons in that BRH bond so that it is developing that partial negative. The hydrogen is developing a partial positive. There's no equal and opposite force to cancel, so we do end up with a polar molecule and a dipole as it's known. Number 3, Br2, another case where we have a linear molecule because we only have the Br bonding with the Br, and those lone pairs don't contribute to the molecular geometry. So we have a non-polar bond because the bromine-bromine bond is with itself, so there's an equal and opposite match there, and therefore we have a non-polar bond. Finally, for silicon tetrabromide, we have 4 electron groups around that central silicon. So we have SiBr bonds, 4 of them. The electron domain geometry is a tetrahedron, and also the molecular geometry is a tetrahedron because there's no lone pairs on the silicon, and therefore we do have a net cancellation because each of those SiBr bonds is polar, but they exactly cancel each other out, which is a common theme. If you have all the same bonding partner for your central atom, you're going to have a nonpolar molecule if there are no lone pairs, and at least for the cases we see, if you do have one or more lone pairs on the central atom, you'll always end up with a polar molecule if you have polar bonding. That's not always true in chemistry. As I mentioned, some of those higher geometry electron domain groupings like octahedral geometry, you can end up having lone pairs that cancel as well. So fortunately for you, it's relatively straightforward here. If you've got one or more lone pairs on the central atom and you have polar bonds, you're going to end up with a polar molecule. If you have no central atom lone pairs and all the bonding pairs are to the same other atom, then you'll end up with a nonpolar molecule, whether you had polar bonding or not. Alright, if this is still an area that you're struggling at, please do try some additional problems. There's lots at the end of the chapter. There's also the homework set with some nice questions there to help you get the hang of this. And if it's still not making sense, please do reach out to me. As I've said, this is the most important topic for what you'll do in 142 if you're going to be taking that second semester sequence with me. Okay, so good luck, study well. Hopefully it's all coming together for you, but if it isn't, please do reach out for some help.